distributions. And we're going to move into continuous distributions. Okay? And they're really the only one that we're going to spend any time talking about in great detail. Well, it's not 100% true. The one we're going to spend most of our time talking about is what's called the normal distribution. Continuous distributions. Okay? Again, the idea being is a discrete. You could have 1, 2, 3, 4, 5, or whatever. With a continuous, it could be anywhere on the spectrum, right? Where are you at? I'm right here, I think. Okay, well, good for you. Okay? Now, the normal distribution, which I love this. I can't wait till someone comes along and says, you can't use the word normal anymore. Oh, my God, what's normal? I feel like you're judging people. Yep. This girl a couple years ago, she's like, well, I was telling my story like I always tell about the prom and then the counting and stuff, you know, and she's like, and I said, this is one girl. And anyway, she said something about her prom date or whatever. And I'm like, this one girl, and I said something about how the reason I said no to her or why I would not. And she's like, are you judging her? Yeah, just so we're clear. Yeah, exactly why I was judging her. Well, Mr. Groom, I feel like that's bad. I'm like, I don't care. So the normal distribution goes from negative infinity to positive infinity. Now, at some point, there's nothing out there. Okay? Clearly, these head toward 0. Now, if you've had any calculus at all, the area under this curve, which is an integral, if you don't know what an integral is, don't panic. Don't freak out too bad. Or if you've seen it, but it freaks you out because you hated calculus, which I'm sorry if you did, because calculus is fun. The integral of this normal PDF function, if you integrate from negative infinity to infinity, is 1. Okay? That's this fact. Okay? In fact, that'll be true for any continuous distribution. The only difference would be if it's not normal, it'd be some other kind of a function. But you would integrate it from negative infinity to positive infinity, the answer would be 1. Or in other words, what? 100%. Okay? That's it. That's every possible thing can be in there. Okay? Now, a couple things come to my mind. If we're talking about heights of women, what's the probability that a person is exactly 64 inches tall? Exactly 64 inches tall. Well, I know math teacher. Oh, wait, yeah, I am. What's the probability, if I integrate this function, f of x, let's say, dx, and what's the probability I integrate from 64 to 64? What's the area? 0. That's right. Because for to have area, you'd have to have width, yes? So there's two ways to remember that. If you're a calculus person, you remember that if you integrate from a to a, that the answer is 0. Okay, that's one way to do it. For the non-calculus people, or the people who took calculus and been like, it kind of sucks and I hated it, whatever. The better way of thinking about it is this. If I gave you a good ruler, and then a better ruler, and then an atomic ruler, nobody's really 5'3", are they? Right? There's really nobody on the planet who's 5'3", because with a better ruler, I will say that you're 5'2", point yada 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 yada, and this person is 5'3", point yada yada. In other words, there's a zillion possible combinations. There's actually a million. Back up. There's actually an infinite number of them. And 1 divided by infinity is what? Basically. What is 1 divided by infinity, if you want to think of it that way? 0. Think about that. One person, if you had one pizza and you invited all of Portland over to have some, how much would they get? Nothing. And then, but Portland's not even a big city, so you invite like the entire world over, all 7.2 billion or whatever it is today, and literally nobody gets anything. You're splitting atoms, and it's a nuclear war, and it's horrible. Whatever. Anyway, so nobody gets anything. So the idea of 1 divided by infinity is 0, yes? So therefore, the probability of any one value is straight up 0. So regardless of whether you want to think of it that way, which I think makes intuitive sense, or whether you want to think of it from a calculus standpoint, makes no sense. No difference to me. It works the same either way. Now, good news, you do not have to integrate. It's great news, okay? So you will not be doing that. Now, I'm going to show you this just because I feel like if I don't, I feel like I'm a bad teacher. This is the equation for a normal distribution. Come on, Jay, you can do it. Yeah. No, that's not right. There's a square there somewhere. Yeah, that's right. Yeah, that's right. Go ahead, quickly, let's integrate this thing, really, shall we? No, we can't. Why not? Because in reality, this is an e to the x squared function. That function does not have an integral in closed form. It does not have an antiderivative. Okay, it's not possible to integrate it. That's the good news. Okay, now in Calc 2, that was not good news. In Calc 2, you're like, oh my God, now what do I do? Well, you use numerical solutions. Okay? And so in Calc 2, maybe you learned about the right-hand rule and the right-hand sum, the left sum, midpoint sum, Simpson's rule, something that's dripping off in your memory banks probably at some point. And if you don't remember, that's totally fine. But the idea here is the calculator, the computer is going to be able to find inner areas for us. Okay? So what's going to happen is this. In our calculators, in our computers, we're going to use what's called the normal CDF only. All right? You're never going to use the PDF function. There is a normal PDF in your calculator. It's only meant for graphing purposes. Okay? You're going to talk about the normal CDF, and this is a big deal. You're going to be integrating, and you're always going to start on this side over here, because remember, a normal, any kind of CDF is the probability that x is less than or equal to some value, yes? So you're going to basically be saying, hey, what's the probability that you're from here over to here, yes? And so you'd be typing in this upper bound, because it's always going to start at this lower bound of negative infinity, and it's going to add up all the way until this value you told it to get. But what if I wanted this area? Then you're going to subtract from 100%. Okay? Just like we did before. What if I wanted the area between here and here? Well, I'm going to find the area from here all the way down. I'm going to find the area from here all the way down, doing two separate CDFs, and then subtract them. By the way, just exactly like you do in calculus, right? In calculus, you all had Calc 2, right? Yeah, more or less. And you vaguely remember it? Sort of? Sort of? Let's just pretend for a minute that you do, right? If you don't, just nod your head and go, oh yeah, totally, sure. So back in the day, you take the antiderivative, yes? Oops, try again, stupid. You take the antiderivative, yes? And then here and here. And then you take f of b minus f of a, right? Well, f of b, for our purposes, would be the probability from here all the way down. F of a will be the probability from here all the way down. So the difference will be this piece in here. That's what I'm looking for. Okay? Now, technically speaking, whenever you just do the CDF, what it's going to do is it's going to go from negative infinity all the way up to b in this case, yes? Now, at negative infinity, how much has showed up at that point? Nothing. No, not much. It's nothing. At negative infinity, nothing has happened yet. Yes? That is the farthest that you can go to the left for you people. And nothing has happened yet. And as I start coming to the right, I'm picking up probabilities. I'm coming along, yes? And then it's building and building and building, and then it peaks and it goes back down and basically goes to 0 on the far end over there. But it adds up to 100%, yes? So the idea here, this guy would just be, this is what we get the normal CDF for that b value, yes? That upper bound value, if you will. We're going to talk about how to put that in later on. For the lower value, of course, it'd be from negative infinity to a. Oh, now what? Look at that, you jinxed us, pal. Messed up. As soon as you came in, the computer decided it was going to hate me. Cool. Try that again. And again, it's going to be f of a minus 0. Yeah? That's the idea. And then if I want the difference between them, I just take and subtract these two values, right? And find the difference between them if I want to do that. Couple things. Again, the hard part about this is, well, hard/easy part. This is Calc 2 to be hard. This thing does not exist. The antiderivative does not exist. You cannot find it. There's no such animal for e to the x squared. So, good news, bad news. So, I'm going to be using the CDF function to actually find that area. Okay, it's going to be doing it for me behind the scenes. Suffice it to say, it's just doing this integral for me behind the scenes in numeric values. Okay? Now, number one, that's number one. Number two, the normal distribution 100% defined by distribution is defined by the mean and standard deviation. So what we will say is it's normal and mu sigma, like that. Okay, so if I tell you that it's normal, 200 pounds and 14 pounds, what we're saying is this distribution has a mean of 200, so right here, 200, and a standard deviation of 14, so 214, 228, 242, and well, I don't know, like 186, 172, 158, I guess, right? Hey, that looks very similar to the empirical rule we did before, yes? Because it is very similar. The difference is before, we only use these whole values for number of standard deviations above and below the mean, right? So, but today, the fun begins because then we can be any value between the mean, anywhere from here to there to here to there to anywhere. Okay? You may recall, and let's just remind ourselves of this, in here, how much probability is in here? Between 1 and negative 1? Standard deviations? How much probability? Percentage-wise. The empirical rule. 68%. Beautiful. That's right. Within 1 deviation of the mean. That's right. Within 2 deviations, how much? 95. And within 3, 99.7. Yes? Sweet. Where did they get those numbers from, Jay? I'm here to help you. Let's figure it out, shall we? Now, what's that? That's what I'm saying. So what they're saying is this. They're saying that from here down is how much? From here down is how much? Well, I don't know, but I do know that from here, this is 34% right here, yes? Right? So then it would be 16% from here on down, yes? Because that's halfway, right? How far is it from here down? Well, I don't know. It's 50 to the middle, yes? Plus 34 more? It'd be 84% from here all the way down, yes? So 84 minus 16 is 68. That's exactly how that comes about. Okay? And we'll do that on the computer in just a minute. It's going to be a good time. All right. Now, there's just one more small thing, then we'll take a break, and then we'll spend the rest of the 2 hours-ish discussing the rest of this and doing examples. It's going to be awesome. All right. So you recall we did z-scores before, yes? What did z-scores tell us? Kind of. So how many standard deviations, right? Above or below the mean you are, right? So are you 3 deviations above? You'd have a positive z-score, z3, z equals 3. If you were 1 below, your z-score would be negative 1, and so on. Why do we do that? I'll tell you why. We talked about that before. We talked about standardizing scores. So we can compare things that are different, right? We're saying this one is 1. In this population, you're 1 standard deviation above the mean. Over here, you might be 0.9 standard deviations above the mean. One might have a bigger standard deviation and a bigger mean. Whatever it is, all we're saying is relative to this population, maybe you're 0.9 standard deviations above the mean. We're standardizing it. So it turns out that the z distribution, or if you will, the standard normal. Standard because we standardized it. Normal because the shape is the same. The standard normal will look like this. 0, 1, 2, 3, negative 1, negative 2, negative 3. and we've standardized it. We no longer have to keep track of the money, the dollars, the weights, the whatever. 214 pounds. Forget 214 pounds. That's positive 1 for a z-score. Okay? And this guy right here, for instance, how much is between here and here? Still 68%. Are you with me? But in the last one, it was like this, Jay. It was 200 pounds and 186 and 214. That's right. But it's still 1 standard deviation, yes? So it's still 86% of the population. Okay? So what's going to happen is this. When we do these guys, when we make z-scores, what we're saying is this. If I had a mean that was equal to, what did I say, 200? There we go. And a standard deviation that was equal to 14. If I take every value I have and I subtract 200 from it, what does that do? What does that do to our average? What does that do to our average? If every person weight in a room was taken, subtract 200 off of it, you weigh significantly less than 200, you would get negative value for your weight, yes? Some of us would be positive still when you subtract 200 from us, yes? And when you put it all together, where would they all clump around now? They wouldn't clump around 200 anymore. They would clump around where? Well, the old mean was 200. They'd clump around 0. That's right. This is exciting. So instead of clumping around 200, they would now clump around 0. But notice the standard deviation is still 14 pounds. This is no good. I don't want to have a standard deviation of 14 pounds. So what I'm going to do is I'm going to divide by the standard deviation. So instead of being this, now it's going to be clumped around 0 with a standard deviation of 1. No, there, I fixed it. That's what we're doing when we do these guys. Okay? And we're going to do this to every single problem. Now, engineers / IT / programmers, you are the worst students for this particular thing. Okay? And I don't mean that in a bad way, I just do. It just is what it is. The computers have some built-in functionality for using the original mean and standard deviation. Please don't do that. It will lead you astray down the line. So always make z-scores for everything. Okay, get in the habit of doing that. It will help you down the road, I promise. Okay? So what will happen is there is a way to type in the original standard deviation and the original mean. And you're like, well, I can just type it in, Jay. I just want to do it. Okay, yeah, technically it might work for some things for you right now. But later on, you're going to go, golly, I wish I'd have practiced with that whole z-score thing. I really wish I'd have thought about that a little bit. Okay? I promise. Okay? So trust me on that just a little bit. Okay? I'm not going to lead you astray, I promise. Okay? So what we're going to do is every time we do a problem, we're going to ask some probability question. It's always going to be something like this. What's the probability that x is bigger than some value? Let's just say bigger than some random value. I don't even know. I don't even care. And what is x is distributed? We'll write like this. This means x is distributed. Normal with some mean and some sigma. Okay? What we're going to do is we're going to transform this from being x's to being z's. So we're going to rewrite this as the probability that z is bigger than some big z value. Okay? I'll explain what I mean by that later on. And what we're going to say is that z is always distributed this way. We're going to use this stuff here because it's easier to deal with. Now, in the old days, we did it because in the back of the book, you could give you a normal distribution table. And you could look it up. By the way, it's unfortunate. In the 21st century, there are people who I know that teach statistics. And if you look in your... Oh, I didn't bring my freaking book tonight. In the middle of your book and in the back of your book, there's the normal distribution tables. You'll see them that kind of pops open to them, yes? Oh, yeah, there they go, kind of, I think. Anyway, there's a bunch of them in there. And you're like, oh, isn't this exciting? It looks like this. I'll pop one up here. Left my head at home, too, except it's attached to me. Z table. Z table looks something, give or take, like this guy. Give me that. Give it to me. They look something like, give or take, one of these guys. Like this one, or like this one. Oops, not that one. Yeah, that'll work. That'll actually play. And no, I don't need to have to do it for dummies. Give it to me. Oh, yeah, well, that'll work, actually. View image. View image? I don't care. No. All right, well, I was trying to show you the picture. If I could just find a dang picture, I'd be pretty happy. There it is. Cool. Nice. Here's one. Nice. So back in the old days, you'd kind of play Battleship with this deal. I need negative 1.27, bloop, and you'd read it off the graph, and you're like, that's what the probability would be. You did this because you could not do every single possible thing. The computer can do it now, but it's still, this is a very helpful thing. Not this chart, but the idea of using z-scores is very helpful later on for other things, okay? So once you get the hang of it, it makes yourself a lot easier, I promise, okay? Notice that it goes all the way over to 100% on this guy. If you look up here, it actually goes up to 99.99999 or whatever, right, percent. At the far end down here, 0.00003. In essence, there's nobody down there, okay? And we'll be dealing with some data like this going forward. All right, let's take a quick break, and we'll get back at it in a minute. It's going to be a good time. We'll pause this. So, oh, that's weird. All right, so suppose you have suppose X is distributed this way. And again, it could be weights. I'm going to go with weights just for fun. But again, they're just distributed this way. I did hit record, I think. Yep, it's going. All right. Nice. It's hard to say. So what is the probability that you take a randomly selected person, okay, just take a name out of a hat. What's the probability that this person weighs less than 192 pounds? Okay? It's all in pounds, of course. Pounds. Okay? And how am I going to do this problem? Well, the first answer is I don't know. Okay? But I will say this. I'm going to convert this statement from a probability about X to a probability about Z. So pretty much going forward, if it's a normal distribution problem, if you're not converting it to a z-score, you're doing it wrong. Okay? So number one. So let's do that. Let's make a z-score. So z equals, it's going to be 192 minus 200 over 14. Again, this person weighs 192, weighs less than the mean. So it's going to end up being a negative z-score in a minute, yes? So it's going to be negative 8 out of 14, which is 4/7, which is negative 0.56 or something. Is that true? Negative 0.57 almost, isn't it? 4, am I right? 1.4. About 0.57, isn't it? Yeah. Nice. So this thing here, the probability X is less than 192 is equivalent to Z being less than negative 0.57. Okay? For the first couple problems, I'm going to keep drawing a problem every time. Okay? So initially we said we were here. 200 is here. Okay, we were here. Here's 186 is here, of course. 186, that's one full standard deviation. We're about here. 192. Okay? I want to go from here down. That's what I need to find. Clearly, it's less than 50%, yes? Okay? Going to keep those things in mind as you're going along, okay? So every time for the first few times, I'm going to keep redrawing them exactly the same way. So here is 0. Here is negative 0.57 of a standard deviation. And we're going to find the probability that you're from here down. These are equivalent probabilities. They're exactly the same amount of space when you're dead said and done. Okay? But I want to deal with them as if we're only going to use the z-scores. We're going to go find this guy right here, right now. But this is the exact same answer as that guy up there. All right. Questions on that? So take your calculators. Well, we'll start with Excel, and I'll do the other calculators too. Get on there. So here I'm just going to give it one of these numbers. So equals norm dot s dot dist. This is kind of a big deal. The S means standard normal. There is a norm dist. The norm dist takes into account your original mean and original standard deviation. Use the .s1, please. Okay? So notice it asks you for the z-score. So negative 0.57, comma 1. Always, comma 1. In fact, it irritates me that they ask me if I want it to be cumulative or not, because the probability of exactly 0.57 is a big fat goose egg. So why are you asking about it? Okay? I would like to find a person who programmed this and kick him in the backside. Always 1. Okay? I hit enter. Hey, it's 28 point some odd percent. Okay? Now, if you looked at Jay's picture over here, you're like, that looks a lot more than 28%. I feel like you're wrong, Jay. Yes, pictures can be deceiving, yes? So this is why, as we start these things, I kind of like to look at some real pictures that are evenly balanced appropriately. So if I look at GeoGebra that I showed you last time, oh crap, just a minute. GeoGebra, I forgot they changed where they're hiding that. Probability, there you go. It looks like this fella. And again, I think it's just nice from the standpoint of just for visualization purposes. So look, normal 0, 1, that's awesome. I want, notice that it says, when I click on this fella, it says less than or equal to this amount here, yes? This is where I'm going to put in the negative 0.57. Negative 0.57, hit enter, and it's 28%. Now, notice that it's now shaded better, because we're saying it looks a little better. I mean, this looks more like 28% than it did in my picture a minute ago, in other words, okay? So don't get hung up on that, like, oh, I think you screwed it up, Jay. I don't know. They're sketches for me. But this is a little better way of thinking about it from that standpoint. Kind of makes sense, because we already said what happens if this was negative 1. From negative 1 that way would be 16%, yes? So we're somewhere fairly close to that. So, 28%, I'd buy that. So here's the question. The question was, to us, stated, what's the probability that a randomly selected person weighs less than 192 pounds? There's a 28% chance of that happening. They are equivalent things. So you could ask, what's the probability? Or you could ask this question, which is more likely to be asked of you. What percent of men in this population weigh less than 192 pounds? 28% of them do. Because remember, percentage, proportion, probability, potato, vodka. Okay? It's just totally up to you what you're thinking about in that case. Rarely does the average person think in terms of probability. A lot of times they'll think about what percent does this, what percent does that. And then they'll screw it up too, by the way. One of my best friends I teach with does not teach math, cannot do percentages to save his life. Literally cannot do a percentage to save his life. Every couple of years he'd come down to me and go, so I have like 1,000 points, Jay, so far, and I want to make the final worth 10% of the grade. I'm like, cool. He's like, so I want to make it 100 points, right? I'm like, well, no, because then it'd be 9% of the grade. What do you mean? I'm like, well, now you'd have 1,100 points. He's like, well, yeah. And like 100 out of 1,100 is 9%. He's like, are you sure? Yeah. And literally every year we had this rehash twice a year, because we do it first semester and second semester. But the new program now, you can just tell it that it's 10% of your grade, and it does it for you behind the scenes, which is always fun too, because this kid, some of the teachers do not ever check that, and it just changes things. And this kid goes, I turned in one assignment yesterday, Mr. Groom, in my class, in this other class, and it's just an assignment, and my grade jumped up like whatever points. I'm like, so they're not weighting it appropriately, right? So they have to go. The kids are telling the teachers, you're not weighting stuff appropriately. So it's just awesome stuff. Okay? Now, same group of people, same men, 214. What's the probability, or what percent of men weigh somewhere between, I don't know, 180 and 206. This feels like I might need to have 2 z-scores, yes? So what I'm going to have here is the probability that z sits between 2 z-scores in a minute. Okay? Now, quick question here. Does it matter if I include the equal to's or not? Does it matter if I include them or not? A normal person would. A normal person would think that. And normally you'd be right if it was a discrete distribution, yes? But because it's continuous, the probability that it equals 180 is 0. So whether you include it or don't include it doesn't make any difference, right? Because it's continuous. Okay, so don't be weirded out by that. So let's make two z-scores. So 180 minus 200 over 14 is negative 20 over 14, which is negative 1.83, I think. 1.87. 1.86? Did I suck at math? Oh, I was thinking divide by 7, not divide by 14. Gotcha. Negative 1.42. Yeah, I'll buy that. Sorry, I think I was dividing by 7. And Z2 would be equal to 206 minus 200 divided by 14, which is 6/14, which is 0.42. Nice. So this statement here is equivalent to this statement here. Okay? So in Excel, this is how this would get done. We would do the following. We say equals norm.s.dist. And oh, by the way, something that some people like to do, and it's totally up to you how you do it. I'm going to do equals. I'm just going to show you this. This is totally up to you if you want to do it this way. I find that sometimes this makes my life easier. Sometimes it does, sometimes it doesn't. If I'm doing a whole bunch of these, okay? In other words, I just pick some random cell over here, yes? Yeah? And then I could put something in that cell. So initially, I could put in negative, what was the first one? Negative 1.42. So 0.077. Okay? And then here's another fun trick. If you're doing a bunch of these guys, you could just copy that down and then put in 0.42 here. What? So in other words, the idea is that you just kind of keep dragging that thing along, makes your life easier. Sometimes it does, sometimes it doesn't. That's why I like Excel, because I can set up however I want to do it. Okay? So I could have a whole column where here's my different z-scores I'm typing in, and the next column over will be the probabilities. So my answer is going to be the difference of these two guys. So 0.66 minus 0.077, I'm going to get 58%. So again, over here, what that picture looks like is this. Just shut up on me there. That's a disturbing picture, sorry. It's like a tsunami wave or something. All right, here's 200. 206 is going to be right in here somewhere. And 180 is going to be down in here somewhere, yeah? So I don't know what percent is in here. That's what I'm looking for, yes? Which is equivalent to this guy, which is 0, negative 1.42, and 0.42. These areas are the same. Okay? The difference being is this one's going to go a little higher. That's where the rest of the area is going to come from because you've squished it down. Okay? But don't worry about my pictures per se. Just let's look at that. So what we're saying here is this. If you looked on that spreadsheet, from here down was like 66%, yes? That's what this top one said, right? And then the other one, oh, fart. The other one said 7.7%, and that's from here down to 7.7%. So if you want the difference, just subtract the two things, yes? So we said the answer should be 58%. In other words, 58% of all the men in this group will weigh somewhere between, we say, 180 and 206. Nice. Nice. Question?
Do you have to get the 7% in Excel?
Yeah, in Excel. So it's right here. So it's equals norm.s.dist of negative 1.42, comma 1. Remember, that's probably it's your less than or equal to negative 1.42. There's only 7% of the population or less than that. Yeah? Bottom cell is the difference between those two. So 66% minus 7%. Okay, so what we're saying is right here. On the picture, from here down is 66%, yes? from here down is 7%, right? The difference is 58%. Or whatever I said, 59, whatever. That doesn't sound right. 50. Yeah, I guess it's 58. That's what the computer said. I'll believe it. This is beautiful. Oh my gosh, this is beautiful. This is beautiful. Right here. This right here. This is the probability that x that okay, I'm going to write two ways. I'm going to say the probability that x is less than 206, which is the same as the probability that z is less than, or I quit putting equals there, stupid. Go away. Just a minute. I'll finish writing this and then we'll go over it. That x is less than 0.42. There's a 66% chance that's less than that. Okay? This guy up here is the probability that x is less than, what did I say, 180? Which again is equivalent to the probability that z is less than negative 1.42. 7% chance of that. So between them is the difference. Okay? And it's just doing numerical, all it's doing is numerical approximations for integrals. On your TI-89s, the TI-89 is pretty cool for this because on the 89, if you do CDF, it'll ask for a lower bound and an upper bound. Okay? So if you're using your calculators, this is kind of a big deal. So if you're using the TI-89, it'll ask for the mean and the standard deviation. 0, 1. Leave those alone, okay? So make sure you're doing z-scores in this case, okay? And then it'll ask for a lower bound. So you would put in your case, 1.42 negative, and an upper bound, 0.42. Okay? You could do that one in one fell swoop if you're on your TI-89. Okay, and you still should get 0.58, yes? Negative 1.42. And then upper bound, 0.42. And 0, 1 for the standard deviation and the mean. Yep. 58. Yep, that's it, exactly. Yeah, that part's easy. That part's easy. I just remember what I'm supposed to type in. Negative 1.42, comma, 0.42. Yeah, there it is, just like that. If you leave it blank, it assumes it's z-scores. Oh. Okay? But if you did comma, 200, comma, 14, would screw this answer up. You could put it in, but that's what I like about that one because the default is normal, standard normal.
Awesome.
Mm-hmm.
Thank you.
Questions, comments, concerns? Yeah. All right. Let's do this. Let's ask the great googly moogly. Normal distribution. I saw this the other day somewhere of IQs. Nice. Nice. Here we go. Cool. Nice. And it says something like this. Most IQs within 15 points of a median score of 100. That's great. Whatever. Oh, this isn't the one I wanted. What is an average IQ score? Hang on. Let's back up. I saw the one the other day where it actually told me the normal. Does IQ follow the normal? Yes, it does. Yes. Well, come on. Where is that, Jay? Okay, let me just type it in differently. Mean, standard deviation, IQ, US. Yeah, what's the standard deviation? This is, 15 points. 15 points. Yeah, so 115. So, if you knew what your IQ level is, which I don't know what mine is, and I honestly couldn't give a rat's patootie one way or the other, what percent of people have IQs less than 120? I don't know. So it turns out that IQs are distributed normally, a mean of 100, standard deviation of about 15. Okay? And so 120, well, what we're saying is this. If you're drawing a picture out, here's 100. Here's 115, that's one standard deviation. So 120 is just a skosh beyond that. And so I'm looking for all this area. It better be more than 50% when I'm done. In fact, if you're coming from here all the way down, it should be 84%. So it's going to be a little bit more than that. Okay? So let's think about that. So our z-score is going to be equal to 120 minus 100. So clearly that's more than one standard deviation. It comes out to be like 1.33333, I think. And so what the question's asking, what percent of the population are less than 120? That's equivalent to saying z is less than 1.33. Okay? They're equivalent statements. So on my computer, I'm going to do over here somewhere, and I get rid of that and type in 1.33. Oh, I like my surface. Nice. And so if you look at it, that came out to be 91% roughly of the population has an IQ less than 120. Okay? And so it's kind of an interesting deal, I guess. So 0.908. That's it. They are equivalent answers. Okay? On that problem, it's just straight less than, straight greater than, whatever. You just have to do one answer and you're finished. Okay? Clearly that means that 0.092 of the population are what? .092 are greater than 120, right? Again, greater than or equal to, greater than, whatever, because 120 does not exist, okay? Well, the probability that you're exactly 120 is 0, okay? So regardless, you're going to have to do some subtraction once in a while, dink around a little bit here and there once in a while and see what happens, okay? Nice. Now, IQs make no difference to me, all right? I've met some dumb people in my life. They might have high IQs, but they're just functionally weird when it comes to the settings I've dealt with them in. Other people are, who knows? I just don't care anymore. I, honest to God, don't care. Just stay out of my way, work with me, whatever, I don't care. It doesn't make any difference to me. But, again, I keep coming back to things that you see around you every day, right? So, weights of people are hard, they're tricky for weights, but heights are something that you cannot get away from. So in the United States, it turns out that the average height of men's heights are distributed normally. They have a mean of about 70 inches and a standard deviation of about 2 inches. Okay? 5'10", deviation of about 2 inches either way. Okay? So you can look at this a couple of ways, but a person could ask you this, hey, what percent of the population, what percent are taller than 75 inches, okay? Which is, 6'3", which is what I am, okay? People say, Jay, you're tall. I'm like, I don't know. I don't feel that tall. Both my kids are taller than me. Well, the oldest is 6'6", so walking around with him, I feel like a little shrimp, and it's creepy. And I hate it because I can still cross over him on a basketball court. I can still break his ankles off, and then the sucker just swats me out of nowhere. I'm like, God! Their long arms come out of nowhere. And you can feel them coming, too, and all of a sudden it's just like, whoop. Although I swatted him 3 times yesterday. It was pretty funny. All right, anyway, so here we go. So I'm going to go on a limb and say not many people are taller than me nationwide, yes, in the U.S. So 70 is here. We already know this going in, 72, 74, right? That's most everybody. And 76 over there, freak shows over there, okay? So 75 is right here. I don't feel like I'm freakishly tall, but notice that gives me a z-score of what? Now, it's obvious to look at it here, but the z-score is 75 minus 70 over 2. It is a 2.5 standard deviations, yes? Z-score of 2.5. So what I'm looking for is the probability that z is greater than 2.5 standard deviations. That's what I'm looking for. I don't have this on my calculator. I don't have this. This is the opposite of a CDF, yes? I only have less than 2.5. Okay? So I'm going to bring out my calculator. And again, whichever version you have and want to use, it's up to you. And so, again, I'm lazy. I have this baby set up. I'm going to put 2.5 right there. Woo! Look at that. Look at that number right there. 0.99379. That is the percentage of people that are shorter than me. Okay? Of men. So then equals 1 minus that, right? Would be the people that are taller than me, yes? And so you're like, Jay, only 0.6% of the population are taller than you. Yeah, that's right. So how is it you don't feel tall? Because I hang around with a lot of people that are taller than average, yes? And so it's one of these situations of what group are we in? Are we talking just random normal people out in the population? Or are the people that you hang around with taller than the average? So I think a lot of people that I hang around with in my daily life are taller than average, which is why I feel shorter than average, because the average of the people I hang around with is maybe my height or something, okay? In other words, I hang out with taller people, I guess. Okay, that makes sense? So when you look at these things, kind of keep that in mind. Remember the normal distribution, you're always comparing yourself to a group. The question is, which group are you in? So just random people on the street, I am ridiculously taller than all of them for the most part. The people I hang out with tend to be taller people. I tend to be more the average height than the people I hang around with for whatever reason. Well, partly because I bred two of them, I guess. But then the rest of them are just, I don't know, apparently I have tall friends. Okay? And so just be aware of that going in. Just keep that in your back of your mind. By the way, if you were like going to fill out a Match.com form, if you're a lady, you're like, or whatever, you're like, hey, look, the dude must be at least 6'3". Like, that's your bottom line, no shorter. What have you just done to your potential dating partners there? You pretty well cut them down to 0. And they must have this, and they must do this, and. Okay, there's nobody left. Okay? It wasn't made to start with, and you've just killed it. There's nobody left in the thing. Okay, that's it. You're done. So this is why, when you say, look, I don't want to put any filters on there. Any height, I feel high. Okay. Okay, there you go. So pretty much anybody is for good. If you say, if I said, the guy must be somewhere between, let's say 5'4", which would be 64 inches, and 74 inches. You're like, okay, maybe oddly specific. 72, let's do 73.1 inches, just to be odd and weird. I mean, it is Portland after all, right? Cool. Have you really restricted things much? I don't think so. Let's just look at this. So, here's 72 inches, right smack dab in the middle. Here's 70. Yeah, pretty much everybody is right. 68, 66. Now, 64 is freakishly short for a dude. Freakishly short. That's really, 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 really short. Have you really cut off anybody on the lower end? Not really. There's like 3 people down there somewhere, maybe somewhere in the U.S., but there's not very many of them over there. So you've not hurt yourself on that end. On this end, you're at 74 inches right here. So you're right here. This is interesting because if I make my z-scores, 64 minus 70 divided by 2 is negative, no, that's not right. I said 64? Did I not minus good? No, it's because it's supposed to be 72, you idiot. There you go. Negative 4 deviations, yes? Yeah, negative 4 deviations. And on the other end, for your Z2, you will see that it is 74 minus 72 over 2. Oh, it's supposed to be 73.1. That is 74, but my value is 73.1. 73.1. So 73.1 is going to give me 1.1 divided by 2. Was that 0.55? I feel like that's right. All right, good. Now, let's do this on our calculator. If you go into your calculator, and I'm just going to use this the way I have it set up here. I'm going to type in negative 4 right here. Maybe I am. Give it to me. Come on. Oh. This thing doesn't snap in like it used to. There you go. Negative 4. Oops. Oh! Look how many people, look at them, how many people are shorter than 5'4"? How many dudes? 0.00000003. That's the probability that you're shorter than 5'4". So it's not going to happen. You literally cut nobody off, right? There's nobody down there. Interesting. Now, watch what happens. If you keep going down there just for fun, what if you went 6 deviations? It's still basically 0, yes? It's still basically 0. It doesn't change much at all. So I'm going to put this back to negative 4 just for fun. I'm going to point something out about that in a minute. And this is going to be what? 0.55? Nice. Notice that these two numbers here are for all intents and purposes the same, yes? Right? Because there's nobody less than this fella, really, right? There's really nobody less than this guy. So you're saying if I go from -4 all the way to negative infinity, I've basically got nobody. That's right. That's right. And so it's basically 71% of the population, right, is what you're looking at. That's what you've cut off and said, these people I'm okay to date or whatever, okay? And you've not really restricted yourself on the bottom end at all, okay? It's interesting to think of it that way. Again, if you put in negative infinity right here, so like negative a lot, the computer will finally just say, screw you, I'm just going to call it 0. So negative, if you were 1,000 or 10,000 deviations below the mean, which doesn't even make sense, the computer goes, screw you at 0. Okay? What's that? And then some. Yeah, exactly. I feel like a 5 foot grown man. Like if you're like 5 foot grown man, that'd be like what, 6 standard deviations below? No, 5 standard deviations below the mean. That's a unicorn, and then some. Okay, so it's kind of interesting to think of it that way. Kind of see where you stand out. Okay, something else to think about is this: if you were, and again, ladies, you can play with this one if you like. We'll do the ladies one this time. Ladies, their heights are distributed again normally. The difference being is what? It's not about how much spread out, because the spread is almost identical. It's about 2 inches for both. The difference is their average. Turns out the average is about 66 inches for women in the U.S. Okay? So if you were to do this, okay, and you were to say, listen, I am, I don't know, how tall are you? 5'7", let's say. So if you were 5'7", okay, here's my question to you. What's the probability that X is less than or equal to 5'7"? Well, I would do this. 67 minus 66 over 2 is a half, obviously. So over here, I'm just going to type in 0.5. And I get out, the answer is 0.69. Now, what does that say to me? It says to me, here's the average, which is 66. You are here at 67. 69% of the population is shorter than you. You're like, well, hey, that's a lot. It is a lot. Well, I'm not even that tall. No, you're not that tall. But you're taller than average by a considerable amount, yes? Now, what do we call this when I tell you that 69% of the population is less than you? What do we call that? No, well, you have a weird definition of freak, lady. I feel like... No, I feel like when I say freak, I'm thinking like nobody's bigger than me, like 1% is bigger than me. Like, okay, that's weird. You're freakishly tall or whatever, right? I feel like the 31% of the population is taller than you. I don't feel like you're that weird. You with me? Isn't this a percentile? This is basically a percentile, as what we did before, yes? In other words, you are in the 69th percentile height-wise, right? You can see where you fit. For instance, myself, I'm in the 99th percentile, which I don't feel like I am, but that's out of the general populace, okay? It does sound cool. Yeah, it does. Yeah, whatever. Who cares? That and $1 will get you a cup of coffee at McDonald's, right? So it's really exciting. Yeah. Nothing you can do about it. The only reason I talk about height is because it's easy to see. Yes, it's easy to see. Like, if that person is such and such tall, oh my God, that's amazing. Yes, it is. That's weird. That's freakishly tall. If I say I want to date someone between here and here, that's kind of weird, Jay. Yeah, you're right. Exactly right. That'd be kind of a strange deal. Oh, by the way, check this out. If a person were to go on Match.com, and again, women's heights, let's just say 66 and 2, if you will, and the person has a weird taste in women's heights. I mean, for instance, like, this is what he's saying. He's like, oh, okay, 66, whatever. 64, we know this kind of thing laid out like this, 60, whatever. And 68, 70, and 72. Listen, the guy says, listen, I'll date women between 5'11 and 6 foot. That's kind of oddly specific. 5'11 and 6 foot. And I would date women between no, between 61 inches tall and 63 inches tall. Why? I don't know. It makes a good math problem. That's why. Okay. Now, how do we go about doing this? Obviously, this becomes a problem where you deal with it in 4 pieces. Yes? So you deal with this piece in here. You deal with this piece out here. Suffice it to say the guy put himself in a bit of a corner. Yes? There's not a lot of people that meet this particular weird criteria. Okay. People always laugh at my problems, but then they have some weird things that they're into. So I don't know. This is just what I'm saying there. Okay. All right. Now, clearly in this situation, okay, on the lower end, what do we have over here? We had 63 inches. Well, 63 minus 66 divided by 2, negative 1.5. And then 61 minus 66 divided by 2 is negative, it's a 5, you moron, negative 2.5. So over here I would type in negative 1.5 and negative 2.5. And I would see there's about a 6% difference. I'm subtracting backwards, but 6% of the population. Oops, come back here. This is 6% of the population are lying in here. Okay? On the other end of things, we know this is a z-score of 3 right here, yes? That makes this guy here a 2.5. So I can come in here and write in 2.5. I can put in 3. Nope, that's a 5, dummy. Nice. And so there's 0.486% of the people are over here. So that's exciting. 0.48, is it 0.48? 0.0486. There you go, dummy. So it's about, this is 0.06 and that's 0.04. I have about 10% of the population available to this person to go date, yes? Almost 11%. Woohoo! That seems weird. Okay, one shouldn't probably restrict oneself. Okay, nice. These probability problems are so nice and so easy. Easy money to work out. Okay? Questions, comments, concerns on those? You good? You good? All right. Again, not very difficult. Question? Good. Now, what I would do if it were me and I was at home and I'm doing some of these and I'm like, I get an answer, it doesn't seem right, doesn't feel right. A person could come in here and this is the between one, if you will. You can click these little bars and doodads and drag them around. I find that a little annoying and off-putting. So I usually just type it in. And, I don't know, negative 1.5, for instance. Hit enter. And then there it is. There's your 6% down there, right? Again, it still maybe doesn't make you happy to think about that. Looks like 6% of this total, but it is. Right? So I blame it on the engineers in this the programmers of why it looks crappy. I don't know. Let's work here. Something to think about too. If you click this button up here, not that button. I'm sorry, I lied to you. Where's the other button at? Oh, this button here. I'm sorry, that button. Yeah, there it is. Oh no, go back. Yeah, there it is. The idea here is this. This is where the probabilities are adding up. So notice if you start over here at negative infinity, if I drag this dude back over, basically there's no probability yet, yes? In other words, probability that you are less than negative 4 is basically 0, yes? As you start coming this way, probability starts to increase, yes? But slowly, 12%, And right there in the middle, right at the mean, it should be 50% exactly. Notice it's continuing on up, so it's continuing to add probability, but it's not adding very fast. And up here, it's basically 100%. Yes? And once you get out here to 4 point whatever, the computer just says, screw it, it's 1. Because it basically is 1. Okay? Again, I think that's nice to kind of double check myself, see how I feel about things. We're going to see the next couple weeks some different applications of the standard of the normal curve. Suffice it to say that the entrance to Freakville on both sides is approximately 2 standard deviations. Approximately. Okay? So this would be a z-score of positive 2. If you're taller than that, bigger than that, fatter, shorter, smarter, slower, faster, dumber, whatever it is, you're kind of freakish. And if you're on the negative 2 side, same thing. Okay? That's about where the freaks begin. Now we say about because it depends on how judgmental are you. Yeah. So sometimes we say, listen, I feel like I'm going to be really, really super judgy today. And I'm going to say, you're just a little weird, but I'm going to say you're really freaky. So what will happen in that case is we'll move the welcome to Freakville signs. They'll get moved in this way. And you'll be fewer standard deviations from the mean before I say, no, that's enough. You're weird. Okay? Other times we'll say, no, we're not going to judge. Just come on in. This is Portland after all. Okay, I feel like. And we'll actually shoot those guys out a little farther before we say, no, you're too weird. Okay? What will often happen is this. In your typical hard science classes, where you're doing some chemistry, some physics. Although the other day, this sub was in my classroom the day, and the kids were really talking to him, and there's something happened, and he goes, one of them said, that's okay, because physics isn't an exact science, or something like that. I'm like, that's a good one. That's a great one. Awesome. But in a hard science class, typically the cutoff we're going to see later on is 1.96 deviations. Why that? We're going to talk about that in a second, okay? And another one that'll come up is about 1.645. That's another one that comes up all the time. And then another one is 1.28. That's another one that comes up, and not very often though, a little bit. And then 2.57. This one is pretty much restricted only to the sociologists and the psychologists and the soft science, make you feel good type people. All right? Oh, I feel like. That's because they deal with people's feelings and weirdnesses. And because of that, they're never going to be as exact as when you pour some kind of gookumpucky into some other kind of stuff. Chemistry says this must happen every single time. Yes? And so we can be very precise about those. So we're going to use the 1.65s, 1.645s, and the 1.96 a lot. The 2.57 is usually for things like psychology. Okay? Because you have to be pretty weird to stand out, okay, in that situation a lot of times. Okay, so let's do this. I think this is the last one I'm going to talk about tonight, and then we're just going to get out of here and see what happens. Here is negative 1.645, and here's positive 1.645. What percent is in the middle here? How did I figure that out? Well, what I'm really asking is, what's the probability that z is between these guys, yes? Well, I don't know. Let's find out. So, get in there. Oh, there's one more thing I want to talk about, but just take a jiffy. 1.645 and negative 1.645. Oh, look at that! What percent? I subtracted backwards. Ignore the negative. 90%. Right on the button. Right on the button. Does that make sense? So negative 1.645, I should do it the right order so you don't freak out. Negative 1.645 and positive 1.645. 90% almost on the button between negative 1.645 and positive 1.645. That is going to be a big deal later on. We're going to talk about this a ton later on. We're doing confidence intervals. We're doing some other things. We're going to be using the 1.645 values a ton later on. Okay? What about between negative 1.96 and positive 1.96? Well, if this one's 90, what do you think this one's going to be? Take a wild stab. I feel like I moved the goalpost out a little ways. So is the percentage going to go up or down? It's going to go up. Well, it doesn't have very far to go. So what if you were a betting man? What would you bet on it being? It was 90% before, and you move it out and it goes up. What would you think? 95%? Yeah, it turns out it is 95%. And here's how we know this. Oops. If you come back in here, negative 1.96, positive 1.96, 95%. Right on the button. Nice. Wait a minute. Didn't we learn by the empirical rule that 2 deviations was 95%? No, we said it was approximately 95%, yes? 2 plus or minus 2 is pretty close to plus or minus 1.96, yes? So approximately 95%. That's good. Now, there's one more. Let's talk about this 2.57, dude. Now, if you're going to move the goalposts out to here, what percent do you think it would be? Take a wild stab. What's that? 99.7. That's what I'm hearing. Ooh, that was dumb. No. That I erased it, I mean. Could be 99.7. Could be. Any other ideas? Because I think 3 deviations was 99.7, yes? So 2.5 might not be 99.7, but it might be 99. Just 99. Just 99. Let's see what happens. Let's see what happens. Oh, did I already write the answer? Darn it. Negative 2.57 and positive 2.57. 98.9, so 99%. Mm-hmm. Yeah. And some books I think actually write it as negative 2.58. It's kind of in between the two of them. And if you do that, it's a little over, yes? It's in that ballpark. Okay. Nice. Okay, there's one last thing I want to talk about. It'll just take a second. I almost spaced off. That would really have irritated me if I got home and then realized I forgot to mention it. That would just really suck. All right. Turns out that the slowest, the lowest, the whatever, the lowest, let's just say the lowest 15% of math kids based on state test are going to get an extra math class, going to get more help or something. Okay, that's cool. On the state test, the average might be 2,800, and the standard deviation might be, what are you doing, stupid? Standard deviation might be 350. Cool. Where would the lowest 15% be? I mean, here we have right here 2,800, right? Okay. So it's somewhere over here, yes? I don't know where, right? I want to know this cutoff score, if you will, yes? Here's what we're going to do. We're going to make ourselves a z-score. Every time? Literally every time. Here's what's going to happen, though. We're going to find what z-score corresponds to 15%. You with me? Here's how we're going to do it. Now, on the computer here, you're going to go equals norm dot s dot inverse. Oops, that's not onverse, inverse. There you go. Q. And you're going to type in the probability that's in the lower tail. So in this case, 15%, yes? The probability that's less than, so 15%. Okay? Now be careful of that. What if I wanted the upper 5%? You wouldn't type in 5%, you type in 95% because it's the area to the left. Okay? That makes sense? It's always area to the left. Now, here we go. What do we get? We got a z-score of negative 1.03. Okay? So over here, we have ourselves a z-score of negative 1.03. What's that going to do for me? Well, I feel like z is equal to x minus mu over sigma, yes? Do I know all that stuff? Well, I know this. Do I know sigma? Yeah. Do I know mu? Yep. So can I solve it? I feel like I can. So when you multiply that over there, it's going to be 350 times 1.03 negative, which is like negative 362. And then it's going to be x minus 2,800. So, of course, it's going to be 2,800 minus 362. $24.38, right? Right? So if a kid scores less than 24.38, he's getting extra special help. Okay? If he scores greater than that, he's fine. We don't care about him, I guess. That makes sense? It's a cutoff score kind of a situation. We do this all the time, okay? Cops might even do this, right? Turns out, and it's true to some degree, although I don't know that they actually do the math on it. But let's just pretend we're a cop who does a little bit of math just for a good time. The average person speeding down the highway towards Sandy, between Gresham and Sandy, the average speed on that road is what about? At least, yeah, exactly. So the speeds might be normally distributed again. 70, standard deviation of 7 miles an hour. Sure. They're going to go catch, they're only going to write tickets for they're going to catch the top, 19% of speeders. Don't know why 19, I just work here. Okay? And so what do they need to know? They need to know a cutoff score. If you're going faster than this, I'm going to pull you over. If not, I'm just going to sit here on the side of the road and watch you go by. Because I don't care. Okay? Okay? So here's this. If I do this, what I'm saying is this. Here's my picture. As the night progresses, they get uglier. They should, in a perfect world, should look like this. And if you might remember back in the day in calculus, you learned about points of inflection, where they change its concavity from being concave up to being concave down. That occurs at the first standard deviation. Okay? So if you've drawn it appropriately, that's what it should look like. I don't really care. Now, here's my problem. I want 19% up here, yes? What percent are less than that value? So I want to know this z-score, but I want to know what, I have to tell Betsy what percent are less than that, yes? So 19 greater than, 81 less than, yes? So let's put that into Excel. And the way to do that again is, of course, this normal S inverse routine. And I'm just going to put in 0.81. Oops. And look what I got. 0.877. That's my z-score. Okay? But watch what happens if I screw this up. And I put in 19 instead. Oh, I love this. This is awesome. Watch this. It's the negative. We love symmetry. Do not retype it in, for God's sake. So all you're going to get the positive version of that. You with me? You're like, wait, I'm supposed to be above the mean. Oh, what an idiot. And then drop the negative and off you go. Okay? Do not sweat this. It is symmetry. It's beautiful. All right? It's oh, I love symmetry. So this is 0.877. And so 0.877 is equal to x minus 70 over 7. Look what you're saying here. You are saying that you are 0.877 standard deviations, yes? Wait for it. Above the mean. That's literally what you just told me. Here's the mean, and you are 0.877 standard deviations above it. That's literally what you're saying. And that comes out to be 75 point something? 76? 76.1. Good enough. So if you score, what are we talking about here? I forgot. Oh, yeah. So if you are going faster than 76.1, coming to get you. All right? You're doing 76, you're golden. You're golden. Because you're not in the top 19% of the speeders. Okay? And, yeah, what? No, I literally don't know. Don't quote me on that one. It makes no sense to me who they pull over, why they pull over sometimes. Good for you. That's not a job I'd want to do. Good for you. But why they pull over, who they pull over, makes no sense to me. Yeah, I mean, sometimes you think, oh, just waiting for the really super fast guys. But who knows? Yeah. By the way, if this were true, and you saw someone doing 95, would they stand out like a sore thumb? Why? Well, why, though? You're totally right, but why? They're almost 4 deviations faster than the average, yes? Right? You can do that in your head, right? Maybe 98 would be 4 deviations faster than the average, yes? You would seriously stand out like a sore thumb, okay? And this is that idea that, how bad do you want to stand out, yeah? So in this case here, 76% or 76 miles an hour doesn't seem that fast because it's not that fast, okay? And there's 19, almost 20% of the population are driving faster than me. Well, I don't feel like I stand out that bad, yes? If I'm in the top 5% of speeders on the road, Right? Well, almost nobody's going faster than me. I'm running past people right and left. You know, if you're that guy that people are kind of passing, you kind of pass, this and that, you're not going to get pulled over probably, unless you're drunk or on your phone or something. Okay. But you're probably not going to get pulled over for speeding. Probably. All right. Unless you're that time when you're going out the gorge and you're passing people and people are passing you and everybody's doing 85 and the cop goes, eeny, meeny, miny, let's go get Jay. All right. That can happen. Sucks to be you when that happens. What's that? Yeah, exactly. So, yeah, anymore, I don't know. But I remember this one time my brother and I were driving on the freeway, and I said, dude, if you get pulled over, he's driving my car. You're right, you're getting a ticket, pal. And I no more said that. We traded drivers 5 minutes later. I get pulled over. He was doing 90. I was doing 74. I got a ticket. Are you kidding me? Whatever. Okay. Anyway, that's just how life goes sometimes. But again, it's that idea of how bad do you want to stand out from the crowd, okay? And we'll talk more about this idea of freaks next week. We'll talk more about the idea of some things with confidence intervals coming up soon. But it's all going to be based on this stuff right here. So, 2 things you'll be doing this week on your homework. You'll be doing questions like this, where you're trying to find probably is less than a value, greater than a value, or between a couple values. And then toward the end, you're going to be asked questions like, hey, what is the top with the lowest 15%? The upper 5%, what would that cutoff score be? That's really the only 2 things you'll have on the homework this week. Okay? So it's pretty straightforward kind of homework. The kind of homework that makes the person feel good about oneself. Okay? What I'm not getting a lot of is I'm not getting a lot of questions from people. And I'm not sure why. Is that because everyone's getting it? Or is that because, well, I don't want to ask? I don't know. But I'm saying if you need questions, you just send me a question and we'll just work it out real quick, okay? Take a jiffy. Yes, sir.
Oh, for the project directions, is it the one posted on the blog website or is it not?
I still haven't made the decision yet. It's not a hurry because it's not a big project either way, okay? It's not a hurry. So, but I will get them to you. Remember, no class next week. I will be posting a video for you to watch though. So be heads up to that, okay?
So next week's week 8.
Oh, Veterans Day, yes.
Next week's week 8.
Is it really already?
Yeah.
Nuh-uh.
So then there's a project due, so we're gonna do that project.
No, it's not week 8 already.
Well, it's week 7 now. So next week is week 8. Well, I have no class.
Val posted directions before next Monday. I'll make a decision and post directions before next Monday, probably with a video, so that you can kind of watch me, not watch me, but listen to me and hear me describe it. That's 0. You will be doing a project. The only question was, because like one of them might...
That's all, folks.